So welcome back to IGC. So from last 2 days, we have been solving some questions from previous year GATE question papers, right? So again, this session, we are back with some questions from 2011 question paper of GATE Aerospace Engineering. And again, we'll be focusing on the questions related to aerodynamics. All right. So let's get started, guys. Uh, yeah. So you can see here the number of questions and the marks that have been allotted to aerodynamics in GATE 2011. Okay, so you can see that there were total around 10 questions that were asked from aerodynamics, and it was for 16 marks, right? So this is the weightage that you can expect roughly around every year. Okay, so let's now get started. Let's look into these questions. Let's see each question and how to solve them, and also try to understand the concepts in and around these questions. Okay, so shall we start? Are you guys ready? Okay, so let's start. Yeah, so here you can see the first question, which was question number 18 in GATE 2011 paper. It was a 1 mark question. It was an MCQ. So let's understand this question and try to solve. It is seen that the drag polar of a certain aerofoil is symmetric about the CD axis. So the drag polar could refer to which of the following airfoils? Okay. So they are talking about drag polar here in this question, right? And they've given you um, 3 aerofoils an option, right? So let's understand what do these aerofoils mean, right? So you see here, they are all named by NACA, right? So they are NACA nomenclatures, what is given, right? So you can see first option is NACA 0012, okay? Second is NACA 4415, and then NACA 23012, which is a 5-digit NACA airfoil, and option D is none of the above, right? So how do we go about this, right? So before understanding the question itself, let's look at the options and try to understand what are the types of aerofoils that each of these options mean. Okay, so just to revise about the NACA nomenclature, right? So the NACA 4-digit nomenclature. The first digit refers to maximum camber. Okay, the first digit refers to maximum camber in percentage of chord. Okay, and the second digit refers to the position of maximum camber. Okay, and the last 2 digits refer to the maximum thickness, right? So all of these are in percentages of chord, right? Right, now let's see the options. Option A says that NACA 001. So the first 2 digits are 0. What does that mean, guys? When the first 2 digits are 0, it means that there is no camber in this aerofoil, right? So an aerofoil without a camber is a symmetric aerofoil, right? So option A says that it is a symmetric airfoil. Okay. Option A says that it's a symmetric airfoil. What is option B? NACA 15, right? So you see the first 2 digits, they have some camber, right? So it says that there is 0.04 C camber maximum airfoil, and it is present at 40% of chord length, right? This is a cambered airfoil, right? This is a cambered airfoil, right? And what about the third one, 23012? This is also a cambered airfoil, but it is a 5-digit series airfoil, right? So you also should revise the nomenclature of 5-digit airfoil. So essentially, Only the first one is a symmetric airfoil and other two are cambered airfoil, right? So in this question, what they're trying to ask is that the drag polar is going to be symmetric about the CD axis for a symmetric airfoil or for a cambered airfoil or for none of these, right? So that is what is asked. So let's try to understand this drag polar. Okay, let's try to understand drag polar. Okay, so what is a drag polar, guys? You would have come across this word in aerodynamics and also in flight mechanics quite often. So what is a drag polar? Drag polar is the equation that is the only equation in fact in aerodynamics that relates your lift and drag, right? So how is lift and drag related through this drag polar equation? It is essentially a parabolic variation, right? Variation is parabolic, correct? So you know CD, okay? CD is the drag coefficient. CD is the drag coefficient is equal to CD naught plus K CL square, right? So this is essentially the parabolic drag polar equation, right? So if I try to plot this in a CLCD curve, right? So if I try to plot this in a CLCD curve, say this is CD and this is CL, okay? So how would this look like, guys? How will the variation look like? It is a parabolic variation, right? So it is going to be parabolic, something like this, right? And this would be CD naught, correct? So this is essentially a parabolic variation of CL versus CD. All right. Now you see that when your CL is equal to 0, okay, that is on the x-axis. When your CL is equal to 0, your CD is CD naught, right? So in this case, your minimum drag is nothing but CD naught, right? Your minimum drag is CD naught. And this occurs where? This occurs at CL is equal to 0. Okay. At 0 lift, your drag is going to be minimum, and that minimum value is nothing but CD naught, the 0 lift drag coefficient. Okay. So in this case, you can see the drag polar is symmetric about the CD axis, right? It is symmetric about the x-axis, which is the CD axis here. So this type of drag polar is usually found in a symmetric aerofoil. Okay, is usually found in a symmetric aerofoil. Okay, is usually found in a symmetric aerofoil. Now, what happens in an asymmetric aerofoil, right? When you have a camber. So generally, when you have a camber, what happens is your CLCD curve, that is a drag polar curve, looks a little bit different. So now what happens when you have a camber? Okay, when you have a camber, generally the minimum drag is not CD naught. Okay, the minimum drag is not CD naught. Now the minimum drag is going to be even lesser than CD naught. It is going to be CD minimum. Okay, the minimum drag is now going to be CD minimum. And where does this minimum CD occur? It does not occur at alpha is equal to 0, but it occurs at some other angle of attack. Okay, so usually when you have a cambered aerofoil, okay, when you have a cambered aerofoil, your lift equation is related by related to angle of attack by a into alpha minus alpha L is equal to 0, right? So when your angle of attack is equal to 0 lift angle of attack, that is when your alpha is equal to alpha L is equal to 0, your CL is going to be 0, right? So when your CL is going to be 0, your CD is going to be CD naught. Okay. So when your CL is equal to 0, CD is going to be equal to CD naught. Okay, but however, this is not the minimum drag coefficient. This is not the minimum drag coefficient. So in this case, how does your drag polar equation look like? In this case, your drag polar equation actually changes a little bit. So it looks like CD is equal to CD naught. It is going to be now CD minimum. Okay, because the minimum CD is the CD minimum. Okay, CD minimum plus K CL minus CL minimum whole square. Okay, so this is how your drag polar equation now looks like. And this is for what type of aerofoil, guys? This is for a cambered aerofoil, right? Now, if you try to plot this, on a drag polar graph, how does this look like? So you can see when you try to plot this in a drag polar graph, this looks like, you can see this looks like something like this. Okay, so you can see that this is your CD naught. Okay, and this is your CD minimum. CD minimum is somewhat lesser than your CD naught. But where does the CD minimum occur? You can see CD minimum now does not occur at CL is equal to 0, right? CD minimum occurs at some different CL. And what is that CL? That CL is the lift coefficient at which your angle of attack is near about alpha L is equal to 0. Okay, so that is the lift coefficient where your alpha is somewhat close to alpha L is equal to 0, not exactly alpha L is equal to 0. Okay, so now you see that for such a cambered aerofoil, okay, for such a cambered aerofoil, the drag polar graph is no more symmetric about the CD axis. Okay, why is it not symmetric? Because of the modification in the drag polar equation. Okay, because of the modification. And this is true for, in general, it is true for the aerofoils that we use in conventional aircrafts. Okay, but you should keep one thing in mind, that because whenever in aerodynamics or flight mechanics we try to use the drag polar equation, we always use this equation, right? The most simpler parabolic form that we know. We never use this equation. Why? Because in most of the scenarios, CD naught and CD minimum are close to each other. Okay, CD naught and CD minimum are close to each other. So the difference does not really make any, it's not really dramatic. Okay, so your drag polar is going to be almost symmetric, but strictly speaking, it is not going to be symmetric for cambered airfoils. It's going to be symmetric only for a symmetric airfoil, right? So now let's go back to the options and see. Now you see here, option A says symmetric airfoil, other option says cambered airfoil, right? So option A should be the correct answer. Okay. So drag polar is going to be symmetric for a symmetric aerofoil. All right. So yeah, any doubts in this question? I hope this is clear. Yeah. So now let's move on to the next question. Okay. So this is again a one marker question. It's a very simple question, right? So you would have read this statement multiple times in John D. Anderson. So it says that the aerodynamic center of a supersonic aerofoil with chord C is located at which location? Okay. So the options are leading edge. Leading edge is at the at x is equal to 0, right? At the leading edge. Or is it located at 0.25 C? Is it located at the quarter chord point? Or is it located at the half chord point? Or is it located at 3/4 chord point? Right? So this is the question. So guys, can you just guess what should be the answer for this? If you have read this before, can someone guess? All right. If not, let's move on to the explanation, right? Let's see. So what is the supersonic airfoil, right? So you have to understand about the supersonic airfoil. So supersonic airfoil is generally not like your conventional subsonic airfoils, which has a rounded leading edge and a sharp trailing edge, right? So the complete flow dynamics, yeah, Devi Prakash, you say that it is one-fourth of the chord, right? No, that is not correct. Okay. Yeah, but I understand. So this is usually when we say aerodynamic center, it's always located at the quarter chord point. That is for conventional airfoils, right? The subsonic airfoils. But here, however, they have asked the supersonic airfoil. So for supersonic airfoil, that is not the case. Okay. So for a supersonic aerofoil, the flow dynamics is entirely different. Why? Because the free stream flow is now supersonic. Okay, the free stream flow is no more subsonic, right? So what is the shape of supersonic airfoil? So supersonic aerofoil is generally a biconvex aerofoil. Okay, it is generally a biconvex aerofoil. Okay, so what is this biconvex aerofoil? Let's understand. So the biconvex aerofoil is actually a derivative of a diamond-shaped aerofoil, right? So have you all seen this type of a diamond-shaped aerofoil? Okay, so it's an aerofoil just like a rhombus. Okay, it's like a rhombus kept horizontally. Okay, so it's a biconvex. It's a diamond-shaped aerofoil basically, and a derivative of this is the biconvex aerofoil. Now, what is a biconvex aerofoil? Biconvex aerofoil also has a similar shape, but the thing it is much smoother. It does not have any sharp, and it has a rounded leading edge. Okay, it's somewhat like this. So this is a biconvex aerofoil. It has a rounded leading edge. Okay, and however, it has a pointed trailing edge, but the shape somewhat looks like the diamond-shaped aerofoil. Okay, so let's understand the flow physics in this case, right? The flow physics in a biconvex aerofoil. Okay. Now what happens when you have a supersonic Mach number? You see a sharp corner over here, right? Let's assume this is placed at zero angle of attack. Okay, this is placed at alpha is equal to 0 degree, right? Now what happens here is that because you have a supersonic flow, you will have an oblique shock like this, right? Because the supersonic flow is now encountering a compression corner, right? This is a compression corner. It has some angle theta. So you will have an oblique shock, right? So the flow comes like this, encounters an oblique shock, the flow will deflect, okay? And again, you see a pointed edge here where the flow is going to expand because it is a expansion corner. So here you will find some expansion waves. Okay. Again, here also you will be finding some expansion waves. Again, the flow will deflect, will go parallel to the surface, and here again you will have oblique shocks, right? So you see the because this is a supersonic flow and it is highly compressible, the flow dynamics is governed by shocks. Okay, the compression or the pressure difference is rather achieved by shocks. Okay, so if you see the pressure distribution over the surface of such a diamond shaped or biconvex aerofoil, the pressure distribution is very simple. Okay, it is not very complicated CP distribution like what you have in subsonic case, right? So you have an oblique shock, post the shock, the pressure is going to increase, right? So the pressure is going to remain constant, right? So if you see, the pressure distribution over this aerofoil, okay, you are going to have oblique shocks, you're going to have expansion fans over here, and again oblique shocks, right? So the over here, say let's say the pressure is P1, here the pressure is going to increase, right? It is going to P2, and again here the pressure will decrease because of the expansion fan. Let's say it is P3. Okay, same thing is going to happen over here. So you see that the pressure distribution is almost constant over most of the part of this aerofoil, right? So What is aerodynamic center, guys? Aerodynamic center is a point. It's a fixed point on the airfoil, right? It's a fixed point which does not vary with angle of attack. So here the resultant of all these forces, the pressure forces, usually will act at the center. Okay, it will usually act at the center. So all your lift will act at the center. Okay, so the center is generally the half chord point, which is C by 2. So the aerodynamic center lies where, guys? Aerodynamic center lies at C by 2, which is at 0.5 C. So please remember, this is a supersonic airfoil. It is not a subsonic airfoil. So the flow dynamics is different over here. And that is the reason the aerodynamic center is going to shift. Okay, it is going to shift. It is not quarter chord. It is now the half chord point, right? And what is this theory known as? This theory is known as shock expansion theory. Okay, I hope you guys would have studied this in your gas dynamics. Okay, shock expansion theory. So by shock expansion theory, the complete flow dynamics takes place over such an aerofoil with sharp corners. Okay, so this is the concept of supersonic aerofoil. I hope this is clear to you all, right? Let's move on to the next question. Okay, so you see the next question is winglets. Winglets are used on wings to minimize what, right? So what is this winglets, guys? What is winglets? Have you all seen winglets on aircraft wings? Can you tell me where is winglets located on an aircraft wing? Those whoever are watching the session can comment. If you have seen a real aircraft, you would have noticed there are winglets on aircraft wings. Can you tell me the position? Where are these winglets located? They are located usually on the wing tips, right? So they are winglets are basically the aerodynamic surfaces located at the, yeah, Sahil, you are right. They are located at wing tips. At the wing tip. Okay. Now, why are they located at the wing tip? What is that happens at the wing tip, right? You all know when you have an aircraft, let's assume this is a sort of a front view of an aircraft or a back view, whatever. So these are the wing tips. You see a vertical type of aerodynamic surfaces, right? These are nothing but the winglets. Okay. Now, why are they located at the wing tips, guys? Because you know, at the wing tips, what happens at the wing tips? What is more prominent at the wing tips? There is wingtip vortices, right? So essentially, there are trailing vortices. There are trailing vortices at the wingtips. Why do these trailing vortices appear? Because of the pressure difference, right? You know, the pressure is going to be higher on the lower surface and it is going to be lower on the upper surface. So because of this pressure difference, and this wing is essentially a finite wing, right? It is not an infinite wing. So to balance out the pressure, these trailing vortices appear at the trailing edge of the aerofoil and they are all concentrated at the tip of the wing, right? So you see such vortices, series of vortices, they shed off from the wing tip of any aircraft, right? Any conventional aircraft. Now, are these vortices good for us? These vortices cause what? These vortices cause induced drag, right? These vortices cause induced drag. Yeah, you are right. They prevent vortex. Yeah. So these vortices generally cause the induced drag. Why? Because there is a downward component of velocity of, that is associated with these vortices, which is called as downwash. Okay. This downwash generally acts downward direction to the lift. So it will reduce the lift, right? So to prevent these vortices, we usually have winglets. So these winglets are some solid surfaces. So they will now prevent this vortices, right? So when you have winglets, you will not see this. It's not that these vortices will not appear; they will appear, but the effect of these vortices will not be so strong that they will increase your drag considerably, right? So winglets are usually placed on the wingtips to reduce the induced drag, right? Now let's look at other options also. It gives you some idea. What is wave drag, guys? What is a wave drag? When does wave drag occur? Can you tell me when does wave drag occur in an aircraft? Wave drag generally occurs at supersonic speeds, right? So when you have supersonic flow of air and suddenly it is say terminated by a shock, so your velocity is going to be reduced to subsonic speed, right? So that sudden drag is the wave drag. Okay. And what is the profile drag? Profile drag is the it is a combination of all such drags like your skin friction drag, your form drag, your interference drag, right? So they are all due to the components of the aircraft, right? They are not associated with winglets, right? Winglets are not used to minimize the profile drag. Skin friction drag is about this how smoothly the air flows over the wings, right? Yeah, you are right. It is drag due to shock waves. Yeah. So skin friction drag is generally observed at very low angles of attack. Okay, at very low angles of attack, when your flow is attached to the surface, because the flow is viscous, you experience the skin friction drag. Even though winglets are there, skin friction drag is still evident. Okay, so they are generally used to minimize the induced drag. So is this clear to you all, guys? Is this clear? All right. So let's now move on to the next question. Yeah. So this question is again a very simple question. We have been doing similar type of questions in past two sessions. So I hope you will be readily able to give the answer now, right? So they're asking that there's a potential flow, okay, potential flow with free stream velocity v infinity over a spinning circular cylinder of radius r and circulation gamma. Okay, the stream function psi where psi is equal to 0 is essentially on the surface of the cylinder is given by what? So essentially you have to find out the correct expression for stream function. Okay. So how do you go about it? Very simple. You know, flow over a lifting cylinder. How is a flow over a lifting cylinder generated, guys? So you have a uniform flow, okay, and you have the flow over a non-lifting cylinder, right? You keep a cylinder in a uniform flow, which is essentially a not it's not non-lifting cylinder, and on top of this you induce some circulation. Okay, you give some circulation to this, or you either rotate the cylinder at some rpm. Okay, so you give some circulation. Let's say the strength of circulation is gamma. So it is a superimposed flow, right? It is a superimposed flow. It is formed by the superimposition of uniform flow, okay, plus a doublet, right? Plus a doublet. What is a doublet, guys? Doublet is a special type of flow which is obtained by placing source and sink at a very close distance, right? And when you superimpose your uniform flow and doublet, you get the flow over a circular cylinder, a normal flow, which is not lifting. On this, when you superimpose a vortex, okay, when you superimpose a vortex, what you obtain is the flow over a lifting cylinder, right? Now, if you want to find out the stream function, expression for stream function psi, what will you do? You have to add up the stream function for individual elementary flows, because you know phi and psi follow superposition principle. Okay, they follow superposition principle. So you can add up the phi and psi for different elementary flows. So you can add up like psi1 plus psi2 plus psi3. Okay, so these are the stream function for the individual elementary flows. Now, what is the stream function for the flow over a cylinder, flow over a non-lifting cylinder? We know it is going to be V infinity R sine theta into 1 minus R square by R square, right? This is the stream function for flow over a non-lifting cylinder, right? Flow over a cylinder, right? Now you want to find out the stream function for just a vortex, a plain vortex, right? So how will you find stream function for a vortex? You know, when you have a vortex, okay, let's say this is a vortex and this is some distance, perpendicular distance to the vortex is r. You know, there is going to be a velocity that is induced by this vortex. It is essentially a tangential component of velocity. That is nothing but gamma by 2 pi r, right? Now, when you equate this to minus dou psi by dou r, you can obtain psi from here, which is nothing but minus gamma by 2 pi ln r plus some constant. Okay, because you are essentially integrating. So you will obviously get a constant. Now, this constant is purposely chosen to be gamma by 2 pi ln capital R, where capital R is the radius of the cylinder. Okay, why is this chosen like that, guys? This is purposely chosen so that your psi is equal to 0 on the surface of the cylinder. Okay, to satisfy this condition, they have chosen the constant by 2 pi ln R. Okay, now you just add up all these psi's. So what will you get? Psi is equal to V infinity R sine theta into 1 minus R square by R square plus gamma by 2 pi ln R by R. Okay, or I think it is the other way around, right? Ln small r by capital R. Okay, so you can now see the options. Option A is the correct answer, right? Now you see, guys, option B and D, if you substitute small r is equal to capital R, okay, that is on the surface of the cylinder, option B and D do not go to 0, right? So not go to 0 for B and D, which means B and D are not the correct answers, right? You can just strike it off. Now you have to decide between A and C, right? I'm sorry, A is not the correct here, it is C, right? Yeah, it is C. It should be sine theta. Okay, so you have to decide between A and C, right? For that, you have to remember what is the stream function for the cylinder, for a non-lifting cylinder. So that is going to be V infinity R sine theta. Okay, so I hope this is clear. It's a very straightforward question. You just have to remember the stream functions. Let's now move on to the next question. Okay, so this is the next question. A low speed wind tunnel has a contraction ratio of 14 is to 1, right? What is a contraction ratio? Contraction ratio is nothing but it is the ratio of area the area ratios between the inlet of the settling chamber to the exit of the settling chamber. Okay, so I hope you know what are the parts of a low speed wind tunnel. Basically, you have a settling chamber first, okay, and then you have a nozzle, right? The nozzle is used to accelerate the flow. So the end of the nozzle is directly connected to the test section. Okay, so basically that uh, nozzle has a area ratio of 14. Okay, and the cross sectional area of the test section is 1 meter square. So this is nothing but the area at the exit of the nozzle. Okay, so what is this? Basically area ratio across the nozzle. Okay, and this is the area at the exit of the nozzle. The static pressure difference between the settling chamber and the test section is 40 centimeter of water column. So they have given you the pressure difference, which is essentially, they have not given you the magnitude directly, but they have told it is 40 centimeter of the water column, right? So you have connected a U-tube manometer between the exit and the inlet of the nozzle, okay? And say in that manometer, the fluid is water and it shows some height difference of 40 centimeter. You can assume G rho air and rho water, this is rho water to be these values. Speed in the test section is dash, right? So it is again a problem of a low speed wind tunnel, right? So quite straightforward. So let's see. You have a settling chamber first, okay, and then you will have a nozzle. Okay, you have a nozzle, and this goes to a test section. After the test section, you have a diffuser and again a constant area duct where it is uh, exposed to the atmosphere. And here you have a fan, right? This is a fan. So this is a low speed wind tunnel in general, right? This is the construction of the low speed wind tunnel. And this you see is the test section. Okay. Here is where you place a model and test it. Now, so let's say this is inlet of the nozzle. This is the exit of the nozzle, right? This is a nozzle. So let's say this is 1 and this is 2. Okay. Let's say there are two stations, 1 and 2. They have given you the contraction ratio. So contraction ratio is the area ratio of the nozzle, which is essentially 14 by 1. Okay, it is 14. And they have also told that the pressure difference between the settling chamber and the test section. Okay, so the pressure difference between settling chamber is this and this is the test section, right? So if you connect a manometer, it will show you the height of the water column, right? So essentially, they have given you P1 minus P2. Okay, you know it's a nozzle, so pressure is going to decrease, right? Because the flow will accelerate. So P1 minus P2 is 40 centimeter of water column. Okay, now how will you interpret this, guys? If it is 40 centimeter of water column, you know the difference in hydrostatic pressure is nothing but rho gh. Okay, so it is water, it is going to be rho water times g into h. So what is this now? 1000 into 9.81 into zero point 0.4. Okay, you can find out what is going to be the pressure difference, right? P1 minus P2. Now you know it is a incompressible flow, right? So let's apply the continuity equation between 1 and 2, right? If you apply continuity equation, you get A1V1 equal to A2V2 because density is constant in compressible flow. So from here, you can say V2 by V1, okay, V2 by V1 is equal to A1 by A2, which is 1 by 14, okay. You know since it is an incompressible and a steady flow, you can also apply Bernoulli's equation, right? So apply Bernoulli's equation. P1 plus half rho 1 V1 square is equal to P2 plus half rho 2 V2 square, right? Rho 1 and rho 2 are the same. Okay. Now remember, rho air and not rho water, because air is the working fluid, right? The fluid that goes in is the air and not water. Okay. So from here, you know P1 minus P2. Okay. So P1 minus P2 is going to be half rho air V2 square minus V1 square. Okay. So from here, P1 minus P2 is equal to half rho air, take V2 square common, minus V1 by V2 the whole square. Okay. You need to find V2 square, right? So V2 is going to be 2 times P1 minus P2 by rho air into 1 minus V1 by V2 is nothing but A2 by A1, right? A2 by A1 the whole square. Okay. So if you substitute all the values, you have P1 minus P2, you have rho air, you have A2 by A1, right? Substitute all the values, you are going to get the answer, right? So can you substitute it and tell me what is the answer that you will get here? So it's going to be around 82 meters per second. Okay. So it was an NAT. Okay. So you can just put the appropriate answer over here. Okay. I hope this is clear. It was a very easy question. Let's now move on. Okay. So here you can see they have given you a boundary layer, right? So it's a flat plate boundary layer question. So yesterday also in 2010 paper, we had one question of boundary layer. So they've given a two-dimensional zero pressure gradient laminar flow. Okay. So, you know, since it's a flat plate, there is no curvature in the plate. Obviously, the flow is going to be of zero pressure gradient, right? The free stream conditions are all given to you. The ratio of displacement thickness to momentum thickness of the boundary layer at a distance of 2 meters from the leading edge. So from the leading edge, you are going to have a displacement thickness, you are going to have a momentum thickness. They are asking you what is the ratio. Okay, so how will we find this? Let's see. Okay, so you have a flat plate boundary layer. Okay, so you know displacement thickness and momentum. Displacement thickness is represented by delta star, right? Theta is the momentum thickness. Okay, so you have to find out the ratio between delta star and theta. Can someone tell me what is this ratio known as? The ratio between displacement and momentum thickness for any boundary layer problem? It is known as shape factor. Okay, is represented by H. So H here is the shape factor. Okay, so they are essentially asking you to find out what is the shape factor in this problem, right? So let's see how to solve this. Okay, now they have not given you any velocity profiles, right? You know the definition of displacement thickness and momentum thickness in terms of the velocity profiles. We can integrate and find out, but they have not given you any velocity profile. But however, since this is a well-established flat plate boundary layer problem, we always have Blasius solution, right? We always have Blasius solution to the flat plate boundary layer problem. According to Blasius solution, he says that delta by x, delta is the boundary layer thickness at any station x, delta by x is equal to 4.9 by root of Reynolds number. Delta star by x is nothing but 1.72 by root of Reynolds number, and theta by x, which is the momentum thickness, is nothing but 0.664 by root of Reynolds number. Okay, so you essentially see that all of these measures of boundary layer thickness are related to the Reynolds number of the flow through some constants, right? These are the constants which was found out by Blasius. So Blasius had done a method of similarity solutions. So this is a general method which is adopted to solve for any boundary layer problem, similarity solutions. So upon solving that, you get these expressions, right? These are the analytical solutions basically. So what is asked is delta star by theta. So you take the ratio of 1 and 2. Okay. So if you take the ratio, what will you get? Delta star by theta is equal to 1.72 by 0.664, which is nothing but 2.59. See, they have asked you to find this at the same x location, right? So x is going to be the same. Because the free stream conditions are the same, your Reynolds number is also going to be the same. So only thing that is changing in delta star and theta are the constants, right? So when you take the ratio, you will get 2.59. So what is the shape factor for a flat plate boundary layer, guys? It is 2.59, right? So you go back, see option B is 2.59. Okay. So I hope this is clear to you all. Let's move on. Okay. Now this question is again a very easy question. It is from lifting line theory. Okay, so let's see what this question says. In the context of Prandtl's lifting line theory for a finite wing, which of the following combinations of statements is true? So the statement P says that the bound vortex is responsible for the lift force. Statement Q says that the trailing vortices are responsible for the induced drag. Statement R is the bound vortex is responsible for the induced drag, and the next statement is the trailing vortices are responsible for the lift force. So essentially, it's trying to ask about the bound vortex and the trailing vortices, right? So I have explained you this in the winglets question. So let's now see this here. Uh, what is it according to the Prandtl's lifting line theory? So consider a wing. Okay, let's say this is a rectangular shaped wing. So you know the shape is an aerofoil. So okay, this is the axis. See, this is a y-axis. Okay, so this is say the span of the wing is say b, right? Now, according to Prandtl's lifting line theory, LLT, okay, lifting line theory, Prandtl models this wing. Yeah, uh, Ajinkya, you are saying it is A. Yeah, it is correct. Okay, let's see the explanation. So Prandtl says that the wing is modeled as horseshoe vortex system. Okay, horseshoe vortex system. Now, what is this horseshoe vortex system, guys? It is like you have a wing. Okay, this wing you are going to have this at the wing tips. You know, because of the pressure differences, there are going to be trailing edge vortices, right? So this trailing edge vortices usually shed down. Okay, so these are the trailing vortices. Okay, and because of these trailing vortices, to satisfy the Helmholtz theorem, right? You know the Helmholtz theorem. To satisfy the Helmholtz theorem, you also have a bound vortex to this wing, okay, which is say in this direction. Okay, this is a bound vortex. So if you see the shape of the vortex system on the wing, it's like a horseshoe, right? It's like this. It's like a horseshoe shape. So this is the vortex system that was proposed by Prandtl. He modeled this on the wing. Okay. So the bound vortex over here is actually responsible for the lift. Why is it responsible for the lift? Because this is the bound circulation which stays on the wing, and according to Kutta-Joukowski theorem, that lift per unit span is rho into V infinity into gamma, right? This gamma is nothing but the bound circulation. Okay. And these trailing edge vortices are responsible for induced drag. Okay. So you see, from the combination of these options, option A is the correct answer. All right. So this is very simple. It was just a conceptual question. Let's now move on. Okay. So the next question, you see that there's a thin aerofoil. Consider a flow over a thin aerofoil at Mach number 0.5. Okay. The Mach number is 0.5 at an angle of attack alpha, using the Prandtl-Glovert rule for compressibility correction. The formula for lift coefficient can be written as dash. Now, when you consider a thin aerofoil, we can in fact use all the assumptions of thin aerofoil over here. The free stream Mach number is given to you as 0.5. The moment you see the free stream Mach number, you should recognize that this is a subsonic compressible Mach number, right? This belongs to a subsonic compressible Mach number. Okay. What is the limit of compressibility, guys? It is 0.35, right? So any Mach number which is greater than 0.35 and less than 1 comes under the subsonic compressible category. Now you have to use Prandtl-Glovert compressibility correction. So Prandtl-Glovert, they have in fact given some rules to correct for compressibility in a flow, right? Because thin aerofoil theory assumes only an incompressible flow, right? So when you do corrections for compressibility, you can modify your thin airfoil theory equations, right? Now, according to thin aerofoil theory, CL can be written as 2 pi alpha, right? For a symmetric aerofoil. For a symmetric aerofoil, it is 2 pi alpha. Now, see, in this question, they have not mentioned anything about the type of aerofoil. So, when you look at the options, we assume that it is a symmetric aerofoil, okay? Because if it was a cambered aerofoil, they should have given alpha L is equal to 0, but that is not there. So, it is a symmetric aerofoil. So, it is 2 pi alpha according to thin aerofoil theory. Now, when you apply compressibility corrections, you multiply this. So, this is CL naught. CL naught is for incompressible flow, right? This is for incompressible flow. When you see the compressible flow, when you include the compressibility correction, you multiply this with a factor beta. Okay, what is this beta? The compressibility factor. This compressibility factor for a subsonic compressible flow is generally 1 by root 1 minus m infinity square. Okay, so now your CL becomes 2 pi alpha by root of 1 minus m infinity square. So substitute the values, guys. When you substitute the values, you are going to get 2 into 3.14 into alpha by 1 minus 0.5 square. Okay. When you solve this, when you calculate, you're going to get 7.26 times alpha, which is option C. Right. So this is one of the common mistake made by people. They do not consider the compressibility correction. But you must remember, whenever your Mach number, the free stream Mach number exceeds 0.3, you must consider the compressibility correction. Okay, so I hope this is clear to you all. Let's now move on to the next question. Okay, So again, the next question is based on Prandtl's lifting line theory. They have given you the angle of attack variation along the span of the wing, right? Alpha of y naught is given to you. So this is nothing but the lifting line equation given by Prandtl. Okay. U infinity is the free stream, alpha is angle of attack, y naught is a span-wise location, alpha L is equal to 0 is the zero lift angle of attack variation along the span, gamma is the circulation, right? So this is how the complete circulation or the angle of attack over the wing is modeled by Prandtl by his equation, right? Now let's see what are the questions. So there are two questions under this. The first question is rate of change of circulation with angle of attack, that is dou gamma by dou alpha. What is the uh, derivative of circulation with respect to alpha, right? So this is, see, this question, when they have given you such a passage, it looks like you really have to depend upon the passage to answer this question, right? But that's not the case. You just have to get the context from the passage, but you can use your own knowledge to answer the question. It is not necessarily that you have to take the data from the passage, right? Now, you know, according to Kutta-Joukowski theorem, right? According to Kutta-Joukowski theorem, lift per unit span is equal to rho into u infinity into gamma, correct? From here, I can write CL is nothing but lift per unit span by half rho u infinity square into C, right? Where C is the chord length. So if you substitute this, you are going to get rho u infinity gamma by half rho u infinity square into C. So this is going to be 2 gamma by u infinity times C, right? From here, you can see gamma is equal to u infinity C by 2 into CL, right? Now you can expand CL according to thin airfoil theory, right? So CL is nothing but u infinity C by 2. CL is 2 pi into alpha minus alpha L is equal to 0, right? So now you have written gamma in terms of alpha. Now you can take the derivative of this. So dou gamma by dou alpha is equal to u infinity into C into 2 pi, right? That's it. Alpha L is equal to 0 is not dependent upon alpha, right? So the derivative with respect to alpha of this term will go to 0, right? So this is what you are getting. Now, can you tell me what should be the answer according to the options? Is dou gamma by dou alpha dependent on alpha? U infinity is a constant, C is a chord length constant, 2 pi is again a constant, right? So dou gamma by dou alpha is going to be independent of alpha. Okay. You can clearly see it does not depend on alpha anywhere. Right? Okay. So I think this is clear. It was a very straightforward. See, to solve this, we have not used the data from the passage, right? So that is not always necessary. Let's now look at next question, which is one of the subpart of the previous question. So it is again dependent upon the passage that was given to you. So this question says, given that CL is directly proportional to this integral, this integral is nothing but again it is a consequence of Kutta-Joukowski theorem, right? Because now your gamma is not constant, right? Your gamma is varying along the span of the wing. So to get the average gamma, you are going for integration. The corresponding lift curve slope dou CL by dou alpha is going to be what, right? So you know CL is proportional to integral gamma of y dy from minus b by 2 to b by 2. Okay. Let's now take the derivative with respect to alpha. So dou CL by dou alpha is directly proportional to dou by dou alpha of minus b by 2 to b by 2 gamma of y dy. Okay. So you can now take this derivative inside the integral. So this becomes dou CL by dou alpha directly proportional to minus b by 2 to b by 2 dou gamma by dou alpha times dy. Okay. See guys, gamma is a function of y, right? Gamma is a span-wise function of y. So dou gamma by dou alpha does not depend on y. So this derivative is a constant with respect to the integral, right? The integral is so this is, you can pull this out of the integral. So this becomes dou CL by dou alpha directly proportional to dou gamma by dou alpha times this integral, right? So if you evaluate this integral, you will get B. Okay. Now from the previous question, we have seen dou gamma by dou alpha does not depend on alpha, right? This is independent of alpha, right? This is independent, and you know B is the span length that is also independent of alpha. So dou CL by dou alpha is also going to be independent of alpha. See the options. Option A is the correct one. Okay. So this is again a very simple question. Okay. You really do not have to rely upon the Prandtl's lifting line equation that was given in the passage. Okay, that was just for your context. All right. So I hope this question was clear to you. So we have now come to the end of the session, right? You can. I hope this session was useful to you all. Thank you. If you have any doubts, please feel free to ask in the comment section. I'll be happy to answer. If not, we can end the session here. All right, so let's end the session here. Thank you, everyone.